So, before we start, remind me that Adrian Carro is dead. We are used to in Germany, he's be working on the line of dynamic social system. So, welcome everybody. Today's speaker is Valentin Flunkert, which is a new postdoc working with the team mainly since a couple of months, and he has recently done his PhD in the Technical University in Berlin and in the group of agriculture. I think he will tell us something about that.
Thank you, Ernesto. And first of all, I want to thank you all for the nice welcome that you gave me at IFISC. And so I want to talk about synchronization in networks with delay and show some possible application to the synchronization of laser systems. So most of the work was done at TU Berlin, and so let me first give you an outline of the talk. So I will give some motivation and why the synchronization in these networks may be interesting, and talk about the way we can analyze the stability of synchronization in these networks using the mass stability function. And then I will talk about this limit of taking a large delay. So the elements are coupled via delay, and when they're separated far away from each other in some sense, then the delay is large. And in this case, the situation becomes very simple. And one can classify the networks which can synchronize, and they have different synchronization properties. And finally, I will talk about the application to lasers. So synchronization, as you probably heard before, is an important aspect of nonlinear dynamics. So there are many applications, for instance, in biology, in the brain. Synchronization effects are believed to be related to cognition and learning, and to also related to some pathological states like Parkinson's and epilepsy. In biology, there are many examples. One famous example is the communication of fireflies, which synchronize to each other and blink synchronously. And in some technological applications like power grids and laser networks, synchronization may also be important. In particular, what I'm interested in is chaos synchronization. So two coupled systems evolve on the same chaotic trajectory. And, well, there's some apparent contradiction because chaos is related to small perturbations being amplified, and synchronization is related to perturbations decaying. But of course this contradiction is only apparent because it's related to different directions in phase space. But there are some possible applications to this chaos synchronization, and we heard the talk by Modeste a few weeks ago, who talked in more detail about these applications. So when you want to synchronize two systems which are coupled via a delay, what you observe is that here, this is set up from the experiments running here. So you have two lasers, and they are coupled to each other via a fiber with some delay. And when you measure the intensities, you see that the cross correlation between the intensities is quite low at zero lag, so they do not synchronize to each other with zero lag. There is some larger correlations actually at the delay time. So, but what you observe is when you mix these signals. So this effectively works like distributing the signals from each laser to both lasers back. when you introduce this kind of feedback, then you observe very high correlations at zero lag, and the lasers synchronize very well. So generally, you can see this kind of behavior that when you have bidirectional coupling with a large delay in this kind of setup, then you never observe chaos synchronization. And when you, however, introduce some self-feedbacks with the same delay, you do see chaos synchronization. And I mean, it's intuitively clear why this setup is easier to synchronize, because if you consider perturbation to one of these oscillators or one of these nodes, then no matter how you perturb the system, in this case, both systems receive the same input. And in this case, they do not. So if you perturb one, the other gets a different feedback than the first one. So, of course, this is somehow easier to synchronize, but the question is, can we explain this in more detail? And what about other networks? So, I mean, in this kind of networks, these arguments are not so simple, maybe. So this was the motivation to look at networks of delay-coupled elements, and for simplicity, I only consider maps here, but the general results also hold for flows. So there's discrete dynamics. We have discrete time. Each node xi has a local dynamics f and is coupled to the other nodes with some time delay. There's a coupling function here, h, describing what is fed from one node to the other, and some coupling topology. So the setup may be very restricted, for instance, if you think about biological applications, because you assume that all nodes are identical and that the delays are all equal, but this is the first, starting point, and for technological applications, so for these laser setups, this may be more realistic to implement. So we're interested in this synchronized solution, and in order to have a synchronized solution at all, this row sum over the adjacency matrix, or this coupling matrix, has to be constant. So if it's not constant, if it depends on the row, then in the synchronized or in the identical state, each node would get a different signal, and then they of course could not synchronize. So this is a condition that there exists a synchronized solution. So if we have this kind of row sum condition, so this matrix.
Sorry, Valentin.
Yeah.
Isn't it the case that in the normal situation this sigma is zero?
Well,
row sum is zero, at least in the master stability function studies, Pecor and Carroll and so on.
Yeah. So I mean, in this setup of Pecor and Carroll, they don't have a delay term, so they can effectively take the netto input and put it into this f. So this is just some way to simplify the overall case. If we would want to do that, then we would have an additional delay term here with some self-feedback. So I think that with this delayed setup, it's actually simpler to have to allow for a non-zero row sum. But you could, of course, include this also in the local dynamics in some ways. So then, in this case, the row sum occurs here, and if it's non-zero, the synchronized dynamics behaves like this. And so if we want to analyze the stability of the So if you want to analyze the stability, we consider the synchronized solution and perturb each node with some small perturbation. Then you can linearize the equation for this perturbation, and the equation looks like this. And in some matrix form with this vector xi containing all the xi I, this looks like this. So this describes all the linear perturbations of the network. And
yeah, just use the digital.
okay. So this variation equations are described in this by this set of equations here, and the idea of the master stability function is basically to well, you can here this coupling matrix occurs, and you can diagonalize this matrix, and what you then get is one equation where the row sum occurs here instead of the matrix G. So this is one of these variation equations. And then there are n minus 1 other equations where the other eigenvalues of G occur. And this equation describes the perturbation within the synchronization manifold. So this tells you whether the dynamics, the synchronized dynamics, is chaotic or not. And these directions correspond to transverse perturbations and tell you whether synchronization is stable or not. So the idea of this master stability function is to not explicitly have the eigenvalues here, but to have some complex parameter here, and then you can calculate the largest Lyapunov exponent that arises from this equation as a function of the complex parameter. So you get some, in the complex plane, you get some function which tells you whether this variation equation has a positive Lyapunov exponent or a negative one. And then you can just insert all the eigenvalues of a network. And this tells you if all these transversal eigenvalues lie in the stable region, the synchronization is stable. So you separate the dynamical problem from the topological problem. So this is well known, and if you also include this row sum here, then you can actually say that if the row sum is in this positive regime, the synchronized dynamics is chaotic, and if it's in the negative regime, it's non-chaotic. So what I want to show you now is that when we have this network and we take the limit of large coupling delay, then this master stability function becomes very simple. So it has a very simple structure, and this is independent of the local dynamics of the node and independent of the coupling function. So this shape turns up, and the structure is like this. It's rotationally symmetric around the origin. So it's independent of the phase in this complex parameter. And there are two cases which we have to distinguish. So either it is negative at the origin. This is shown here in the upper part. In this case, it increases monotonically with the radius in the complex plane, and there's some value for this radius, some distance from the origin where it changes sign. Or the other case is if it's already positive at the origin here, then it's positive everywhere and as a constant. So, here's some examples. This is calculated for a laser system. Here the delay is very small. So what you have to compare this delay to is to the characteristic time scale of the system, and this is around 30 here. So the relaxation oscillation frequency of the lasers is around 30. And what you see for small delays, how to want this line which shows the critical control line, so where the master stability function changes sign, here has some shape, but as you increase the delay, it becomes more and more circular, and already for tau equals 20, which is roughly the time scale of the dynamics, it's already very circular. And when you increase the delay, it becomes even better. So some similar results were also independently found by Otti and also in the group of Wolfgang Kinzel. So what does this structure now mean for synchronizability of the networks? We can make this table which tells us what kind of synchronized dynamics is stable in what kind of network. So let me start with, let's suppose we have some chaotic dynamics and we have a network where there's an eigenvalue which is larger than the row sum. So there's one eigenvalue larger than the row sum in the network. In this case, synchronization is always unstable because we know it's since the row sum is in a region which is positive, and when we go further from the origin, the mass stability function only increases. So we know that if we evaluate the mass stability function at this eigenvalue, it will be larger, even larger than at this point. So we know that synchronization is unstable. And similarly, if we consider non-chaotic synchronized dynamics, so we know the system is non-chaotic, meaning that lambda max evaluated at the row sum is 0 or negative. Then when we go further to the origin, it can only decrease, and so non-chaotic synchronization is always stable in this kind of network. So in this network where all eigenvalues are smaller than the row sum in magnitude. So you have this kind of classification of all networks, and in two cases we need to know this critical radius where the mass stability function changes sign, and in 4 cases you don't need to know that, and you can already say that synchronization will be stable or unstable. So let me give some examples of these networks. So class B and C, these are the classes where chaos synchronization is impossible. You can see that this first motif that we looked at belongs to this class. Also unidirectionally coupled rings and networks with 0 row sum. So in particular, if you have diffusive type of coupling. And bidirectionally coupled rings with even number of elements. So all these networks will never show chaos synchronization if the delay is large. Then there's this class A, where chaos synchronization is possible and non-chaotic synchronization is always stable. So there we have this motif with the self-feedback again, and in general more rings with self-feedback, rings with bidirectional coupling for odd number of elements, mean field coupled systems, and well, there's some more cases. So it's actually easy to classify these networks into these classes. So I just want to sketch how you can show this this structure. So the idea is first to look at the simplest possible case, and that is the fixed point in the synchronization manifold. So the dynamics is trivial. We only have a fixed point, and in this case, the variation equation it looks like this. We have a constant matrix A and a constant matrix B. So then we can make an ansatz for the eigenvalues of this equation, and we have to solve this this characteristic equation. And if all the solutions have magnitude smaller than 1, then the synchronization is stable. So when the delay becomes large, you can classify these eigenvalues. There are 2 different types of solutions. There are so-called strongly unstable solutions, which are shown here. For instance, these are isolated solutions which don't change magnitude when the delay is increased. And there's another type of solution called pseudo-continuous spectrum. So these are all solutions which pile up at magnitude 1. So they are at the boundary of stability at the border of stability and instability, and it depends on whether this curve approaches the circle from the inner side or from the outer side. And so the strongly unstable solutions are easy to see how they occur. So if you assume that there's a solution to this equation with magnitude larger than 1, then this is also a solution of this equation if the delay is large, because if you insert this here, this becomes very small when the delay is large. So you actually end up with this equation with some very small change, and these strongly unstable solutions are just solutions of this equation. So for the other case, this pseudo-continuous spectrum, you can make an ansatz for these type of solutions. So they have magnitude close to 1. So we make this ansatz 1 plus delta divided by tau, and there's a phase angle for the solutions on the circle. And then you can insert this ansatz, and you get these branches of solutions, which are shown here. And then what happens when you change the phase psi in this equation? You just shift the branches up and down. So this doesn't change the stability. When you change the radius r, you shift them right and left, and this does change the stability. So this actually explains this structure. So psi just shifts the branches up and down, and r shifts the magnitude. So what about the other cases? For periodic orbits, the situation is very similar to fixed points. So we can actually write down a very similar equation, and with the same arguments. It also holds for this equation. And for the chaotic case, it's more difficult. What we argue is that there are infinitely many periodic orbits in the attractor, and for each periodic orbit, we can show this behavior, that this law holds, and it's then possible to characterize the attractor via these periodic orbits, and the result can be carried over. This is in general not a strict proof, because there are some limitations when this theory is, can be applied, and so I mean, well, for some simple systems, this can be shown rigorously, I think, but for the general case, I think it's more conjecture. So, for these 4 cases, I said we didn't need the critical radius, but this one case that we're actually interested in is stable chaos synchronization. For this case, we need the critical radius, and this depends on the dynamics of the system and the coupling function and so on. And what we've now recently shown is that there's a relation between the critical radius and the Lyapunov exponent in the system. So if you consider the synchronized dynamics with some Lyapunov exponent, so the dynamics is chaotic, then for large delay the critical radius is actually given by this equation. And to see this, you can make this substitution into the variation equation. Then you end up with this equation, and you have to argue why this term becomes small, or this perturbation to the equation becomes small for large tau. And in this case, then the Lyapunov exponent of this equation is 0, because per definition this is R0, and then, well, you can discuss this perturb equation. And so then we have the following relation. Networks can show chaos synchronization with a Lyapunov exponent lambda m if the largest eigenvalue gamma max is smaller than this factor. And there are 2 possible scaling relations for the maximum Lyapunov exponent when the delay becomes large. There's one case where the largest Lyapunov exponent stays constant. And the other case is when it stays like 1 over tau. So these cases we call strong chaos and weak chaos. In the case of weak chaos, when you increase the delay, the largest Lyapunov exponent becomes smaller and smaller. And in the case of strong chaos, it stays constant. And so then you can see that for strong chaos, the critical radius goes to 0 and chaos synchronization is not possible. And so you can only achieve chaos synchronization in the case of weak chaos. And well, weak and strong chaos can be distinguished by the Lyapunov exponent, which comes just from this equation when you drop this term. So if this has a positive Lyapunov exponent, then the system has strong chaos. So this is actually very similar to the case of the fixed point before. So it's a generalization to the chaotic case.
The strong chaos is a chaos that appears even if it is not open.
No. There's some subtle thing here. This is the Jacobian on the along the trajectory, and the trajectory comes from the dynamics with coupling.
Oh, okay.
So you consider the dynamics with coupling, and then you just look at this variation equation. And if this has a positive Lyapunov exponent, it's strong chaos. So you can see it in this way. If this has a positive Lyapunov exponent, there's nothing you can add here to stop this from being positive. So one more thing that I want to discuss here is the sensitivity to noise of this synchronized solution. There's for chaos synchronization, there's a phenomenon called bubbling, which occurs when the transversal Lyapunov exponent of this synchronized solution is negative. So we actually have stable synchronization, but there are some periodic orbits in the attractor which are transversely unstable. So these orbits may have a different transversal Lyapunov exponent than the attractor. And if these orbits occur in the system, then they can provide something like escape routes. So when the system is perturbed by small noise or parameter mismatch, you can come close to these orbits and actually leave the synchronization manifold, no matter how small the noise is. So, and this phenomenon has been called bubbling, or there's some other names for it. And we can actually also discuss this bubbling here for the system. So we may define a bubbling radius, RB, which, so at this value, the first orbit loses its transversal stability in the attractor. And then we can classify the networks in this way. So if the largest transversal eigenvalue is smaller than the bubbling radius, synchronization will also be stable and robust to small noise. If it's between R0 and RB, then desynchronization can occur for small noise. You will have this bubbling effect. And well, if it's larger than R0, no synchronization is possible. So, I mean, in practice, it's difficult to calculate this RB because you have to look at all the orbits and the transversal Lyapunov exponents. But I mean, you could do this maybe just by trying out the RB and looking at whether bubbling occurs. So this was the first part, the general part about.
Just before you go, I am somehow confused. Like, I don't understand very well the role of tau. Is there anything you can say in general to what happens to the system when tau increases, or it depends on the system? I had the idea that the larger tau, the more chaotic the system. But you have there are cases in which lambda decreases with tau. Is there, you can say something general on the dependence on synchronization and chaos with increase of tau, or it depends on the chaos?
it depends on the case. So I mean, well, there are two possible scaling laws for this lambda max. It may be constant or decrease like 1/tau, but this is only to the first order. I mean, the second order you don't know anything about. So, for instance, in this case here, if you calculate the critical radius in this fashion, so you know that this scales like 1/tau, then approximately the critical radius stays constant. But of course, there are some higher order effects, so that it still depends on tau. And so I'm not sure whether this answers your question.
Maybe one aspect is certainly that still the dimensionality goes up with tau, even if the Lyapunov exponent scale with 1/tau. So in terms of dimensionality,
More unstable modes,
exactly.
each one less unstable.
Exactly.
Okay, so now I want to talk about the application to lasers. And so the motivation here is that the laser dynamics is very, very fast, so that if you couple these lasers over maybe 20 centimeters or 30 centimeters, the distance is already quite large. So when you have maybe a meter or something, you can already say you're in the large coupling regime or large delay regime. So this is actually already the large delay limit. And in this case, we can apply these results from the general discussion. And in particular, we had three conditions here. So the first condition was the constant row sum condition, which gives the existence of a synchronization manifold. The second one is a necessary condition for synchronization, which is independent of the dynamics. But, well, you can classify networks with this, but without looking at the dynamics, but it's only necessary. And the third, well, this should be three. The third condition is a sufficient condition for synchronization, and it depends, of course, on the dynamics on this parameter, this last parameter R0. So the first condition usually, so this constant row sum condition, I mean, usually it's very simple because you just have to add the rows and see whether the row sum is equal. But for the lasers, this is actually a little bit more complicated because you may have some phase shift between the laser. So we consider laser networks with all optical coupling, and here's a simple example of one laser with self-feedback, and it feeds the signal into a second laser which also has self-feedback, and here are the equations for the complex electric field. So you can see the structure of the coupling. You have some coupling strengths, the self-feedback strengths for laser 1 with a coupling phase. Here is the cross-coupling strength with the cross-coupling phase, and so on. But we have to allow this kind of synchronization. So I mean, the phase, there's still this arbitrary phase shift between the lasers. So
you take G as a constant there?
No, it depends on E and N and so on, of course. Yeah. We have to take these phase shifts into account, and the row sum condition then looks like this. So we have the coupling strengths here, the coupling phases, and these relative phase shifts between the lasers. And so we now have to search for all possible values of U which give a constant row sum. So this is somehow, well, it's more complicated, and the sensitivity to this coupling phases has been shown in an experiment in this reference by Ingo and co-authors. So what they looked at here was this coupling motif here, and they varied the relative phase. So this is defined as the phase, self-feedback phase of laser 2 minus the self-feedback phase of laser 1. And what you observe is that you can get very high correlations and very low correlations when you change this relative phase of the lasers. And we can actually explain this with this condition for an invariant synchronization manifold. So this is the row sum condition written out, and you can now, for certain parameters of 1, 1, 2, 1, and 2, 2, for instance, you can look at what kind of parameters allow a synchronized solution, and this is shown here as the blue dotted line. On this blue dotted line, the condition is fulfilled, and here on this side you see the correlation is plotted, and on this side this is the fraction of synchronized time. So basically I look at the difference of the intensities of the two lasers, and if this difference is smaller than some value epsilon, I say they're synchronized, and otherwise they're not synchronized. And then I look at the fraction of synchronized and not synchronized parts in the time series. And when you look at this, you see that the synchronization is completely determined by this condition here. But this is in a regime where the other conditions are fulfilled, so the stability is fulfilled.
What about this shadow you have on the positive slope?
Here? Yeah, it's not. I'm not completely sure. I mean, there may be some higher order effects, but I have to look at this. So similarly, for more complex networks, we can also look at the synchronization conditions. We get some curves where synchronization is possible, and it depends. And we see that the synchronization probability is very high here. In these regions, this is different than the other case. Here, we really have a breakdown of this condition because the stability changes here. So there, we do have an invariant synchronization manifold, but it's unstable.
In the places where you get a very good correlation but not synchronization, what's the behavior?
Yeah, you have some generalized synchronization. So, well, I mean, for instance, here, so this I use this measure because it's very sensitive, and the correlation is kind of not a good measure to find these lines, because the correlation may be very, very high, even though they're not perfectly synchronized. So this is that's why you observe high correlations here. And well, what's kind of interesting is that these lines tend to separate regions of large and low correlations somehow, but I haven't completely understood this yet. So in the other case, this is also similar here. So we have low correlations here and high correlations there. I haven't. I don't know why this happens.
That's interesting because I mean, places where you have a strong correlation are interesting anyway, even if they are not, even if it is a sort of generalized synchronization, just a sort of identical synchronization.
Yeah, true. But these regions, I mean, I cannot analyze. I mean, I can only handle the complete synchronization. But still, if this really turns out to be a general phenomenon that always separates these regions, that would be interesting. I'm sure. So, what about larger networks? Well, these interference conditions, mathematically, they are already very complicated for a few lasers and a few couplings, and experimentally, you would have to control quite a few coupling phases. So this is unrealistic that you can actually achieve this for maybe more than 2 phases. One feasible setup, feasible in question mark, is the following. So we couple all the lasers into some fiber with a common mirror here, and then under the following conditions, so if we assume that each of these paths correspond to a coupling phase. So to get the light from here to here, I get a coupling phase psi I, and from here to there, I get a coupling phase psi 2, and so on. So if we assume that this kind of condition holds, then the coupling from laser K to laser J is the sum of these coupling phases. And if we can also realize that the coupling strength is equal between these lasers, then this condition is enough to synchronize the lasers. So then there's these relative phase shifts of the lasers can arrange so that they give a synchronized solution. But I mean, I don't know how realistic it is in a normal setup that you actually have this kind of condition. So I mean, in a perfect setup you do have it, but in practice I guess it will be more complicated.
Would it be not if phi kj is identical to phi jk?
Say again?
Would it be not if you add for symmetry that phi kj is identical to phi kj?
Just the symmetry you mean?
Yeah, symmetry. Mm-hmm. Would that be enough to make
no, because you have if you have n lasers, you have n minus 1 relative phases of the lasers that can arrange. And in this symmetric case, you have how many 3 degrees in a matrix? You have, well, n times n plus 1/2.
So that's not enough.
So it's not enough. Yeah. And the rest you have to control by changing phases or coupling strength. So one thing that comes out here actually, which I didn't mention, is that so here you see that the coupling strength they can vary. So when you arrange these coupling phases, you can change some mismatch in the coupling strength because the lasers get, for instance, destructive interference if both signals are stronger than what the other laser receives. They can have destructive interference to compensate for this. So there's some more degree of freedom here, but in general you would have to compensate for these other degrees of freedom by controlling coupling strength or phases and so on. So my summary. I looked at this master stability function for large delay and showed that the structure is very simple, and you can then classify networks with respect to their synchronization properties. In some cases you can say these networks will never show chaos synchronization and these will always show periodic synchronization and so on. In some cases you have to calculate one free parameter which depends on the dynamics. There's this relation between weak and strong chaos in the delayed system, which so strong chaotic dynamics cannot be synchronized. And for these lasers, these give some synchronization conditions, and in particular the constant row sum condition becomes very complicated in the lasers due to this degree of freedom in the phase. So my plans for my time here, I have some ideas what I want to look at. So I want to continue to look at delay coupled networks, but maybe also introduce some heterogeneities. So for instance, delay mismatches and maybe heterogeneities in the nodes. And I want to look at synchronization of these networks. In more general, maybe some dynamical patterns which can occur there, and robustness to noise. Some other ideas are related to the control of dynamics in small motifs, whether we can control which kind of patterns, for instance, can occur or not. Lyapunov spectra for delay coupled systems. I'm working on this, and there are some ideas to do this together with experiments to get some results out of the simulation data. And I just started working on these covariant Lyapunov vectors, and so I want to look at these vectors in networks and in delay systems. And if you are also interested in any of these topics, then
first, you will tell us what is a covariant Lyapunov vector.
Okay.
Then I might be interested.
I think so.
So in general, when you calculate Lyapunov vectors with the Gram-Schmidt procedure, you orthogonalize them, and you do get the correct Lyapunov exponent, which tells you how strongly you diverge in different directions, but actually the directions are not correct. because these Lyapunov vectors, well, these are not Lyapunov vectors, but Schmidt vectors. For instance, they depend on the scalar product that you use, and in particular, they are not covariant with the dynamics. So if you have them at one point in tangent space and you propagate them, they don't end up as your Schmidt vectors in the next time step. And there are some vectors, these covariant Lyapunov vectors, which give the correct Lyapunov exponents and tell you the correct direction. So they may not be orthogonal, and they're in principle covariant with the dynamics, so you could just propagate them forward. Numerically, this doesn't work, but and so for large systems, a few years ago there was a paper where they, or actually two papers where they discovered some algorithm to calculate them efficiently, or the largest few, because before it used to be that you had to calculate them all, which doesn't make sense in a system with maybe, I don't know, 10,000 degrees of freedom or so. But so now you can calculate only the largest few of these. So maybe you're
Okay, thank you very much. Questions?
You're applying all of this to synchronization of chaos, but if I remember properly, in one of your at the beginning of your talk, you said that the structure of the Lyapunov spectrum and all that is not. You don't have a rigorous demonstration that this is the case. I mean, you started to have this one. So what is this? So you are applying this to the chaotic case.
Yeah.
Do you have any hint? Do you think this is a real result? Perhaps there are some exceptions, or what is this?
I don't think
any exception of this
no,
here.
No. So I mean, we do have some formulas, and you can, if you know the Lyapunov exponents of all periodic orbits, you can. There's some ways to calculate the Lyapunov exponent of the attractor. So this is usually the Lyapunov exponent of the attractor is dominated by the orbits with small period, and there's this periodic orbit theory where you sum up all periodic orbits and so on. And so we do have some formula, but we're not so sure when this can be applied.
But I think this is. I mean, an orbit can be unstable.
Yeah.
But if the direction of instability points inside the attractor, still synchronization will be stable.
Yeah, so I mean the weights are associated to the weight in the chaotic attractor, so in the synchronization manifold. But you have to look at the perturbation transfers. Well, maybe we can discuss this in more detail. So there's we do have some formula to calculate this, and this we can argue why it should hold, but I'm actually not sure when this formula holds. So the formula has been used before by or developed by Complejos and so on, and they have some numerical, some general arguments why it should hold, and some numerical examples. But I think it's mainly conjecture. So I rely on this conjecture, and it first breaks down. But yeah, it's a good question.
Any other questions? That's not the case. Valentin.